Hello everyone. In this video, I'm going to discuss with you permutation groups in abstract algebra. Let us have a recall. Permutation is the rearrangement of objects or elements in a given set. For example, the set of percent plus ampersand asterisk can be rearranged as the set of plus asterisk percent ampersand. Repetition of elements are not permissible in a permutation. A permutation of a set A is a function phi that maps A to itself, that is both one-to-one and onto. In other words, a permutation is a bijective function. Permutation multiplication as a function composition is a binary operation on the collection of all permutations of set A. Let A be a set, and let sigma and tau be permutations of A, so that sigma and tau are both one-to-one functions, mapping A onto A. The composite function sigma times tau is defined by the following schematic diagram. Take note that we need to apply tau first before sigma. We will denote permutation composition as simply the juxtaposition sigma tau. Sigma tau is a permutation if it is one-to-one and onto A. The action of sigma tau on A must be in right-to-left order. First, we apply tau and then sigma. To show that sigma tau is one-to-one, if sigma tau of A sub 1 is equal to sigma tau of A sub 2, then sigma of tau of A sub 1 is also equal to sigma of tau of A sub 2. Since sigma is given to be one-to-one, thus tau of A sub 1 is equal to tau of A sub 2. It means that A sub 1 is equal to A sub 2, and therefore it is one-to-one. To show that sigma tau is onto A, we let A be an element of the set A. Since sigma is onto A, there exists A prime, which is an element of A, such that sigma of A prime is equal to A. Since tau is onto A, there exists A double prime, which is also an element of the set A, such that tau of A double prime is equal to A prime. Thus, A is equal to sigma of A prime, which is equal to sigma of tau of A double prime, and then equals sigma tau of A double prime. So, sigma tau is onto A. Let us have some example. Suppose that A contains the set of 0, 2, 4, 6, 8, and sigma is a permutation given by 0, 4, 2, 6, 8. Take note that the given permutation is in cycle notation, which means that 0 maps to 4 and 4 maps to 0. 2 maps to itself, 6 maps to 8, and 8 maps to 6. We write sigma in a more standard notation as the following. So sigma is the permutation of 4, 2, 0, 8, and 6. So that sigma of 0 is 4, sigma of 2 is 2, and so on. Let tau be the permutation of 6, 4, 8, 0, and 2. Then, we can now perform permutation multiplication simply by applying function composition. First, we start with 0. And take note that we apply permutation multiplication from right to left. So 0 maps to 6, but 6 maps to 8. Therefore, 0 maps to 8. Next, 2. 2 maps to 4, but 4 maps to 0. Therefore, 2 maps to 0. Next, we have 4. 4 maps to 8, but 8 maps to 6. Therefore, 4 maps to 6. Next, 6. 6 maps to 0, but 0 maps to 4. Therefore, 6 maps to 4. And lastly, 8. 8 maps to 2, but 2 maps to 2. Therefore, 8 maps to 2. And therefore, our permutation product is given by 8, 0, 6, 4, and 2. Multiplying in right to left order, in order to find sigma tau of 0, we need to apply tau first. Tau of 0 is 6, and therefore, sigma of 6 is equal to 8. We have here a theorem. Let A be a non-empty set, and let S sub A be the collection of all permutations of A. Then, S sub A is a group under permutation multiplication. This is the proof. We have shown that the composition of two permutations of A yields a permutation of A. So, S sub A is closed under permutation multiplication. Next, permutation multiplication is defined as a function composition. Take note that function composition is associative. That is, sigma tau of A is equal to sigma of tau of A. Hence, associativity is satisfied. The permutation sigma such that sigma of A is A for all A that is in A acts as the identity element. Therefore, the existence of an identity is satisfied. For a permutation sigma, the inverse function, inverse sigma, is the permutation that reverses the direction of the mapping. That is, inverse sigma of A is to be the element A prime of the set A such that A is equal to sigma of A prime. The existence of exactly one such element, A prime, is a consequence of the fact that, as a function, sigma is both one-to-one and onto. For each A that is an element of the set A, we have mu of A is equal to A, which is sigma of A prime, and that is also sigma of the inverse sigma of A. By associative property, that is also equal to sigma times sigma inverse of A. And also, mu of A prime is equal to A prime. And this is also the same as the inverse sigma of A. Applying function composition, we get inverse sigma of the sigma of A prime. By associative property, we get inverse sigma, sigma of A prime. So inverse sigma, sigma, and sigma, sigma inverse are both the permutation mu. Thus, existence of an inverse is satisfied. In other words, when we perform permutation multiplication on a specific permutation mu and its inverse, which is inverse sigma, we will get the identity element. Let us now proceed to the symmetric group. Let A be the finite set 1, 2, 3 all the way to n. The group of all permutations of A is a symmetric group on n letters and is denoted by S sub n. Keep in mind that S sub n has n factorial elements, where n factorial is equal to n times n minus 1 times n minus 2 all the way to 3 times 2 times 1. For example, take S sub 3, which has 3 factorial or 6 elements. Let A be the set of 1, 2, and 3. List the permutations of A and assign a subscripted Greek letter for each of them. Let row sub 0 be the permutation 1, 2, 3. Row sub 1 be the permutation of 2, 3, 1. And let row sub 2 be the permutation of 3, 1, 2. Also, we let phi sub 1 be the permutation 1, 3, 2. Phi sub 2 equals 3, 2, 1. And phi sub 3 equals 2, 1, 3. Take note that this group is not abelian. Here's the multiplication table for S sub 3. So take note that the multiplication table is symmetrical. The green cells matches with the green cells on the other side. Same with the gray. Next, we have the symmetric group of an equilateral triangle. There is a natural correspondence between the elements of S sub 3 and the ways in which two copies of an equilateral triangle with vertices 1, 2, and 3 can be placed. Because of this, S sub 3 is also called the group D sub 3 of symmetries of an equilateral triangle. We use rho sub I for rotations and phi sub I for mirror images in angle bisectors. D sub 3 stands for the third dihedral group. Remember that the word dihedral means two faces. The nth dihedral group, D sub n, is the symmetric group of the regular n-gon. We have here an equilateral triangle. So there are two ways in which we can reproduce another copy of such triangle. We can rotate the triangle, or we can flip the triangle with respect to one angle bisector. Let us try this out. Number 1, how many elements does the fifth dihedral group D sub 5 has? And then for number 2, given the permutations lambda, which is in cycle notation 1, 9, 3, 7, 5, and omega, which is also in cycle notation, we have here 2 transpositions and 1 cycle. You're asked to find lambda omega of 7. Press pause if you want to answer. Now let us proceed to the answers. For number 1, there are 5 factorial elements, which is equal to 5 times 4 times 3 times 2 times 1, which is 120 elements. For number 2, lambda omega of 7, applying permutation, multiplication, that is equal to lambda of omega of 7. Omega of 7 is 9, and lambda of 9 is 3. Thank you for watching.